In 1961, Peter Franken's team fired an intense red ruby laser through a quartz crystal, which emitted a faint but distinct beam of ultraviolet light. At standard, low light intensities, optical materials behave predictably. In this linear regime, the material's electrons vibrate perfectly in step with the incoming light's electric field. If you sent in a specific frequency of light, the material's polarization oscillates at that exact same frequency. But when a material is subjected to the concentrated power of a focused laser beam, that simple proportional relationship breaks down. The high-intensity electric field drives the electrons so hard they can no longer just vibrate cleanly at the driving frequency. They begin to severely distort, acting as microscopic frequency mixers. This process, called second harmonic generation, proved extreme intensities force light and matter to interact in ways requiring entirely new mathematical models. Second harmonic generation is the foundational process of nonlinear optics. This diagram shows the specific transfer of energy occurring at the photon level. Two incoming photons, both at frequency omega, are annihilated simultaneously. Their combined energy is perfectly conserved to create a single new output photon at exactly twice the frequency, 2 omega. Forcing two photons to combine inside a single atom is just the first step. To scale this up and extract a usable macroscopic beam from a crystal, we must satisfy strict symmetry requirements at the atomic level and overcome destructive wave interference at the macroscopic level. Efficient conversion between frequencies is never accidental. It requires a precise alignment of microscopic spatial geometry and large-scale physical engineering. To find the exact origin of this harmonic frequency, we look at the time-domain equation for the material's macroscopic polarization. The first term, relying on the linear susceptibility chi1, assumes the electron is trapped in a perfect parabolic potential well, moving back and forth perfectly according to Hooke's law. But the second term, governed by chi2, is where second harmonic generation actually originates. In a physical lattice structure, the forces binding the electrons are not perfectly uniform. The potential well does not obey Hooke's law at its edges. The extreme electric fields of a laser push the electron's displacement deep into these anharmonic regions of the potential well. Because the shape of the well is irregular at those extremes, the electron's physical oscillation path becomes mathematically distorted. This spatial distortion of the electron's movement is the literal physical mechanism that directly synthesizes new, higher-frequency optical waves. But an anharmonic well is not enough on its own. There is a rigid geometric constraint required to generate a second harmonic. Many common materials are centrosymmetric, meaning their atomic lattice possesses a perfect center of inversion symmetry. Look at the potential well for a centrosymmetric material. It is perfectly symmetrical. An oscillating field driven into this well can only ever produce odd-order nonlinearities, rendering the chi2 term exactly zero. Second harmonic generation is completely forbidden in bulk centrosymmetric media. To double a frequency, the lattice itself must inherently lack a center of inversion symmetry. Notice how this asymmetric potential well is steeper on one side. This specific geometry permits an even-order polarization response. When we take the skewed, lopsided displacement wave produced by this asymmetric well and perform a Fourier transform on it, a massive spike emerges precisely at 2 omega. The mathematical existence of this new light frequency is entirely dictated by the spatial geometry of the atomic lattice. Getting a single dipole to emit a 2 omega photon solves the microscopic problem, but now we have to create a macroscopic beam. For a beam to form and exit the crystal, the harmonic emissions from dipoles distributed throughout the entire length of the material must constructively interfere. Here we encounter the problem of wave-vector mismatch, denoted mathematically as delta K, which is caused by normal dispersion. A material's index of refraction is frequency-dependent. The index for the input frequency will not equal the index for the doubled frequency. Because of this difference in refractive index, the fundamental driving wave and the generated harmonic wave propagate through the medium at distinct phase velocities. Normal dispersion dictates that the higher frequency harmonic wave will almost always travel slower through the medium than the driving wave. This inherent difference in speed creates a continuous physical dissynchronization that threatens to destroy the harmonic beam entirely. This equation models the final intensity of the generated harmonic wave after it travels a distance, L, through the crystal. The crucial variable is this sinc squared factor, which directly depends on our wave vector mismatch, delta K. This relationship dictates what is known as the coherence length of the material. Because the waves travel at different speeds, after exactly one coherence length, the newly generated harmonic photons become 180 degrees out of phase. This forces destructive interference. Total harmonic intensity oscillates up briefly, then cancels out, never accumulating into a beam. Without engineering intervention to correct this phase slip, generation efficiency drops to near zero. Optical engineers must manipulate the material itself, using birefringent properties or structured periodic polling to compensate for the speed difference and force delta K to exactly zero. Satisfying this condition of perfect phase matching over a long interaction length is the central technological challenge in generating high-power harmonic lasers. While physicists engineer bulk crystals to produce these signals, microscopists use the exact same mathematical constraints to map biological structures. We established earlier that second harmonic generation rigidly requires broken inversion symmetry. Scientists flipped this strict limitation into an incredibly precise diagnostic tool. Bulk fluids, standard cytoplasm, and uniform tissues are structurally uniform. They are macroscopically centrosymmetric. Therefore, the chi-2 tensor in those bulk regions evaluates to zero. When a laser passes through them, it produces no harmonic signal at all. But structural surfaces and phase boundaries are different. Purely by being an edge, a surface inherently lacks inversion symmetry. At the exact boundary of a cell membrane, the symmetry breaks down, and the chi-2 tensor suddenly becomes non-zero. This means researchers can image structural interfaces with absolute zero background noise from the surrounding fluid. The fluid is physically incapable of emitting the light. By isolating this optical response, scientists use the rigid constraints of the nonlinear susceptibility tensor to cleanly map molecular architecture. The quantum origins of harmonic generation restrict where and how these frequencies can form. By mapping exactly where those rules are satisfied, this mathematical limitation becomes an indispensable probe of the physical world.